Hi, my name is Dear Tiagi, and in this video I'll be going over Unit 4 Momentum for AP Physics 1. So to start, let's derive impulse momentum theorem using Newton's second law. So Newton's second law states that force is equal to mass times acceleration. And we know that acceleration is equal to the change in velocity over time. So we can write this as force is equal to mass times change in velocity over time. If we multiply by time on both sides, what we get is the impulse momentum theorem, which states force times delta time equals m times delta v. And this is called impulse, given the symbol J, with units newtons, because force is in newtons, times seconds. And this is given the symbol P for momentum. And this is units is kilograms times meters per second. And also these are both vectors because force is a vector and delta velocity is also a vector. So these are both vector quantities. And this is the impulse momentum theorem, which relates impulse to momentum. Next, so the conservation of momentum states that in a system, closed system, with no external impulses, so no external impulses are acting in the system, i.e. there's no external forces, momentum is conserved, which means that the momentum initial equals the momentum final in this system. Or in other words, MAVA initial plus MBVB initial is equal to MAVA final plus MBVB final. And this is if we have like a cart and a cart colliding, like so. This is an example of conservation of momentum because there are no external forces in the system. If we draw a system with the two carts, the only forces on the system are gravity, but they act downwards and they don't act in the x area. Therefore, conservation of momentum holds, no external impulses, and this holds. It wouldn't hold if we had a situation where we had a collision maybe on a ramp, right? Because now we have an external impulse in that direction, in the x direction, by gravity. Next, let's talk about collisions. So there are three types of collisions. There are elastic collisions. Elastic collisions are where kinetic energy is conserved. So the kinetic energy initial of the system is equal to the kinetic energy final of the system. There's perfectly inelastic. And this is when two objects stick. Here, energy is lost because it's lost due to heat or sound. And we have regular inelastic. Again, in this case, it's the objects don't stick together. No stick. But they still lose energy. Energy is lost after the collision. And so first of all, what is a collision? A collision is a large force in a short amount of time, and it's collision because this large force occurs in a very short amount of time. There's two objects being interacted or affected by that force. And finally, center of mass. So the center of mass is the weighted average location of mass in a system. And the reason why center of mass is useful in physics is because in physics we can describe all forces to be acting on the center of mass. So for example, let's say we have a system, or so let's say we have an object like this, right? And the center of mass is like here. So for the force of gravity is acting everywhere on the system, on each mass particle around it. But because the center of mass is the weighted average location of the mass, we can say that the force of gravity is only acting on the center object here, which is useful when we're doing problems in the future with torque or other kinds of physics problems. So again, center mass, that's where all the forces are acting on in an object. And the formula for center mass is equal to, the formula is x center mass is equal to the sum of the masses times their positions divided by the sum of the masses. And that's the center mass of a system. And also one more thing, internal forces do not change the velocity. Do not change velocity of the center mass, which is something we're going to go into more detail later on. Okay, let's try out some problems now. So for the first problem, let's say we have a guy who's kicking a soccer ball, and he kicks the ball for a time, let's say 0.05 seconds. He kicks it, the ball has a mass of 0.45 kilograms, and when he finishes kicking the ball, at the moment he releases, right, his foot's off the ball has a velocity of 20 meters per second. And we're trying to find the force of his foot on the ball. So we can do this using the impulse momentum theorem, because we can see we have a mass, we have a velocity, and we have a time. So the only thing we're missing is a force, which is what we're coincidentally solving for. So impulse momentum, F delta t, is equal to m delta v. So F delta t is 0.05 seconds. So 0.05 equals mass 0.45. If the mass was changing, we'd have to do delta mv, but the mass usually doesn't change, so you don't have to do that. And then delta v. So our initial v is 0, because the ball is stationary at rest, and then it's 20 meters per second. So delta v is 20, and dividing by 0.05, we get the F is equal to 180 newtons, which is our final answer. So that's an example of a impulse momentum problem. And next, we'll try out a collision problem. So let's say we have a cart here, call it A, cart here, call it B, and the cart A has a mass of 2 kilograms, cart B has a mass of 1 kilogram, and cart A is going at a velocity towards cart B at 3 meters per second. And then what happens is they collide, and cart A ends up continuing to the right at 1 meter per second, and cart B is also going to the right at x meters per second, and we want to find x. Okay, so this is a simple problem of conservation of momentum. In this case, momentum is conserved because even though there is a force when these two collide, right, that force is internal to the cart AB Earth system. And because the force is internal, we can use conservation of momentum because there's no impulses if the force is internal. Okay, so conservation of momentum. So we add up the initial momentums and we set it equal to the final momentums. So the initial momentums is 3 times 2 is 6 plus, so this is stationary, so it's 0 momentum, so it's 0 plus 0 is equal to, this is a mass of 2 going right at 1, so momentum is 2 plus mass of 1 times x meters per second, so this is a momentum of x. Therefore, the x velocity final is equal to 4 meters per second using conservation of momentum. Next, let's try to find out if this collision is elastic or inelastic. So to do that, we have to check if the kinetic initial is equal to the kinetic final. So the kinetic initial is equal to mv squared of all the objects in the system. mv squared of this one is obviously 0. This one's going to be 2 times 3 squared over 2, which is 9. And then for the final system, we have a mass of 2, 1 meter per second squared, which is just 2 over 2, which is equal to 1, plus, and we have velocity of 4, mass is 1, so 4 times 4 is 16, divided by 2 is 8, and so 9 is the amount of joules of energy final, which is equal to the initial, and therefore this collision is is just elastic, because kinetic energy is conserved. And finally, let's do one more problem. Let's say we have an asteroid, and it has a mass of 8,000 kilograms. And what happens to this asteroid is there's a bomb in it, and so it blows up, and the asteroid, one piece of the asteroid is sent to the left. This piece weighs 3,000 kilograms, and it's going at a speed of negative 15 meters per second. And we want to find the speed here. We want to find velocity, the second piece. And again, they're both going linearly in the same two x directions. Okay, so for this one, is momentum conserved? And the answer is yes. Even though there is a force being acted, the force of the bomb blowing up, that force is internal to the system, right? The force, if we draw the system, it's internal. The force is acting within the system. And therefore, momentum is conserved. So our initial momentum is 0 because it's stationary. Final momentum is equal to 3,000 times negative 15. So again, negative 15 because momentum is a vector. So negative 3,000 times 15 plus. So if the mass, total mass is 8,000 and this mass is 3,000, this has to be 5,000. So 5,000 times velocity final, which is what we're solving for. If we rearrange, what we'll get is velocity final is equal to 9 meters per second, which is our final answer. One more question, is the center of mass of this object changing? So initially, we know the center of mass is going to be somewhere in the middle of the asteroid. The question is, what is the velocity of the center of mass in this system here? And the answer is, the velocity of the center of mass does not change. It's stationary here. So it's in the same place here, same place there. And the reason why is because, again, the velocity of the center of mass does not change if there are no external forces acting on the system. In this case, there are no external forces acting on the system. Therefore, the center of mass of velocity, the center of mass of the system's velocity does not change, or the velocity of the center of mass does not change. And that is Unit 4, Momentum. Thank you guys all for watching, and I'll see you guys all tomorrow. Bye.